Namaste. In this learning dialogue video, we'll be discussing about the calculation of inductance from the flux linkages. Okay, in order to calculate the inductance, we will not consider the complex things. We will start with a primitive thing, that is, we will consider a simple isolated current carrying conductor. The reason is, if you assume it's an isolated current carrying conductor, there won't be any other conductor nearby this conductor, so that the flux link with this conductor can be assumed as circular in nature. Okay, if you have any other conductors nearby this conductor, then current carrying conductors, then what happens is the flux produced by the nearby conductors may interfere and the shape may deviate from the circular shape. Okay, so in order to assume that the flux linked with this conductor are circular in shape, we are starting with a isolated current carrying conductor. Okay, let us see. Okay, this is the conductor what we are going to consider, and the conductor having radius of r. Okay, and we are dividing the flux linked with this conductor into two categories. One is flux linkages due to the internal flux. That means the flux linked with the fractional part of this conductor inside the conductor as one type, and as the one case. And the second case will be the flux outside the conductor. Okay, so we are going to consider the flux linkages due to internal flux and the flux linkages due to external flux. Okay, first let us start with the flux linkages due to internal flux. In order to consider the flux linkages with respect to the conductor due to internal flux, we are assuming a infinitely small tubular column whose radius is y and the thickness is dy. Okay, radius is y and thickness is dy. Okay, and since it's a current carrying conductor, it is associated with the magnetic field. Okay, the MMF around a concentric closed circular path of radius y internal to the conductor can be given by your Ampere's law, that is integral of magnetic field intensity with respect to the perimeter of the circular shape, that is this perimeter, that is equivalent to the current enclosed in the tubular column. Okay, so this is by Ampere's law. So let us try to calculate what is this current and how much is the field intensity and all. So if you consider the field intensity around this circular path, it is constant in this direction. In this direction, it is constant. Okay, with respect to ds, it is tangential and it is constant. Okay, so here Hy is the magnetic field intensity given in ampere turn per meter, and Iy is the current enclosed within this tubular column. Okay, so if you integrate with respect to ds, we will be getting it as 2 pi y, which is the perimeter of that circular tubular column, and Hy is constant. So the integral will become 2 pi y Hy is equals to Iy. Okay. So from this, assuming uniform current density, if you assume uniform current density throughout the conductor, then the current density at a particular radius of y can be considered as Iy by pi y square. Okay, this is the area. Pi y square is the area. The current enclosed within that area is Iy. So the current density will be Iy by pi y square, and that is equivalent to, since you are assuming it is uniform current density, if you consider the entire conductor, the current density will be I. I is the current carried by the entire conductor. That divided by the total cross sectional area is pi r square. So Iy by pi y square is equals to I by pi r square, and if you rewrite it, Iy can be written as pi y square by pi r square times I, and if you cancel pi over here, then it can be represented as y square by r square into I. Okay, this is the relation between I and Iy considering the uniform current density. Okay, now if you want to represent Hy in terms of the total current, okay, field intensity, magnetic field intensity in terms of total current, then Hy can be written as just substituting this y square by r square with I by Iy. Okay, so you can write it as Hy is equals to yi by 2 pi r square ampere turn meter. Okay, so this is the field intensity uh, at y meters away from the center. Okay, so the flux density from this field intensity, what you can do is you can also calculate the flux density. Okay, so the flux density By at y meters from the center of the conductor is given by, we know the relation between field intensity and flux density. It is By is equals to mu permeability and Hy. Okay, so field intensity. Okay. So flux density at this point can be calculated as mu into Hy. Just if you substitute this equation for Hy in this, you will get it as mu into yi by 2 pi r square Weber per meter square. Okay, so this is the equation for flux density. Okay. So now moving on to the flux density. Now we'll let us consider an infinitesimal tubular element of thickness dy and length 1 meter. Okay, so till now we are discussing about the same tubular element with radius y and thickness dy. Okay, now let us consider the length also. Okay, 1 meter. Okay, so the flux in the tubular element can be written as d phi, because it's a small tubular column, so d phi can be written as by times dy Weber. Okay, so this is nothing but the equation for your flux density d phi by dy. Okay, so it is by into dy. This is because we are assuming the length is 1 meter. Okay, so it's going to be Weber links, and the fractional terms are going to be, we already calculated Iy by I is equals to y square by r square. Now the total flux linkages can be written as d lambda is equals to y square by r square times d phi. Okay, this is the flux linkage. This is the fractional flux linkages, and this is the flux that is linked with this fraction of the part of the conductor, fractional part of the conductor. Okay, so it is the flux link is change in flux linkage can be written as y square by r square d phi. Okay, so instead of d phi, if you substitute by into dy, okay, and already we have derived the expression for this flux density. Substituting the equivalent for flux density and replacing d phi with by into dy, the flux linkages can be written as y square by r square mu yi by 2 pi r square dy Weber turn per meter. So now we want to calculate the total flux linkages. Okay, we have calculated till now we have calculated the flux link with the tubular column. Now we want to generalize that flux linkage for the entire conductor. So the internal flux linkages can be written as, by taking the integral of the previous equation, in taking the integral of this equation, we can written as, we can write the flux linkages with respect to the internal flux can be written as from 0 to r. 0 means it is the origin to the surface of the conductor, that is r radius. Okay, so you can substitute the same equation in the same equation in the integral, and you can integrate it over 0 to r. Okay, if you integrate it over 0 to r, it will be reduced to mu I by 8 pi Weber turn per meter. Okay, so this is the flux linked because of the internal flux. Okay, so now the permeability mu can be considered as 1 if it is non-magnetic conductor. So then your mu can be written as 4 pi into 10 power minus 7 Henry per meter. Okay, so now if you substitute this in this equation, internal flux linkage will be I by 2 into 10 power minus 7 Weber turn per meter. Okay. So this is the flux linkage because of internal flux, and for this flux linkages, if you calculate the inductance, okay, what is the expression for inductance? It is simple. It is lambda by I, that is flux ratio of flux linkages with respect to I. So if you divide this equation, the inductance due to internal flux can be obtained as 1 by 2 times 10 power minus 7 Henry per meter. Okay, so this is the expression for the inductance due to internal flux. Okay. Now we need to calculate the inductance because of the external flux also. Okay, so then only you can calculate the inductance because of the total flux. Okay, so in the next video we will be discussing about how to calculate the inductance of the conductor due to external flux linkages. Okay.